Awesome. It looks like, Steve, you get to present today. I'm excited you're joining us.
Yeah, glad to be here. Thank you. It's nice to be exposed to this crowd. It's a crowd I haven't really talked with much, and it's good to be in touch.
Yeah, do you know much about what CIRCT's all about? And
I mean, I've skimmed over things. I don't have as much time to dig into the details as I would like, but it's an exciting effort.
yeah, I mean, I think that beyond the code and the things people are building, what we're trying to do is just kind of foster a little community of people who care about moving hardware design forward and applying compilers and new techniques and stuff like that. So it's awesome.
Right. Yeah, and I think this is where things are going. I think this is the pendulum swinging from big EDA back to community-driven efforts. So it's an exciting place to be.
Cool.
All right. Who runs the meeting, Alexi or Chris?
And
me.
Yeah, Andrew.
Andrew, okay.
But I think we can probably declare a forum, and everyone else can be sad they missed your opening.
All right. So should I just jump in, or?
Yeah, jump in. Sure.
Okay.
Sure. What you needed.
Very good. Yeah, so good to meet you all. I hope this leads to discussion, which is the important thing, which apparently that's where I'm starting. But, I might end up filling most of the hour with presentation, but, hopefully this is the first of our communication, and it leads to more. So I'm going to be focused on the modeling abstractions that are inherent within transaction level design methodology. I'm sure some of you have seen some of the material I have online, and some of you have not. So I'll talk about various abstractions. So first of all, transaction level design is the term I apply to the methodology. Then there's TLX is sort of the generic layered approach to adding these abstraction mechanisms on top of an existing HDL language. And TL-Verilog is really the only layering that's gotten any focus. So, the terms tend to be used interchangeably. The particular abstraction mechanisms, I'll start with timing abstraction. And, there are many forms of timing abstraction. I'll talk about the particular form of timing abstraction in transaction level design methodology. We'll talk about a notion of validity, which is an understanding of when the circuitry is doing something meaningful and when it's not. I'll talk about how pipelines interact with each other, and then I'll talk about transactions, which of course is where transaction level design methodology gets its name. And then, as I said, the important part is the discussion, but we have to get there. So usually when I give this presentation or similar presentations, I have several slides motivating the need for abstraction and insulting RTL. I don't think I have to do that with this audience. I think this audience really understands the problem and where the industry is and the need for better solutions. No surprises on this slide, just sort of laying out different layers of abstraction. Of course, we're going to be focused on this transaction level and what that means. The coloring here is indicating that register transfer level in most designs today are using RTL methodology. And the RTL model is serving as essentially the golden reference model, proving the functionality. That effort happens register transfer level and above, and for the most part, correct by construction below the RTL. At a very high level, the goal and the approach of transaction level design is to encapsulate a higher level of abstraction. That abstraction is still cycle accurate, but it doesn't have a lot of the implementation details of exactly when operations are performed. And it's cycle accurate in the overall sense, but we'll talk more about the timing abstraction within that. The physical partitioning of the model and things like that. So we've got this inherent transaction level model describing the behavior, and that becomes the focus of verification. And but you know, in large part, unlike other high-level modeling approaches, the goal was for the designer to be able to retain control over the design at the register transfer level. And we do that through mapping. So we sort of create this separation between specifying behavior and specifying the implementation of that behavior, so that the bulk of design effort can focus above the, you know, the behavior line. We can raise that. So just looking at a little more detail, you know, today's methodology, RTL based, verification energy is focused here. The verification models live at a higher level of abstraction, and through various mechanisms, we need to correlate the higher level models with the RTL model. You know, more formally in the models here on the left, less formally with things like specifications and performance models and so on. And with transaction level design, we're raising the abstraction level of the verification effort. We're also reducing the size of these arrows, right? The TL model is closer to the abstraction level of the verification models, in some cases replacing them. And we use these various mappings to control the register transfer level. So that the absolute, you know, model itself, there are strong benefits there, but the real benefits come from the fact that the model is changing. It's not a static design that is the focus. The design process is a process of, you know, evolving process. The model is constantly changing. You've got even multiple implementations that are implementing fundamentally the same functionality, but with different implementation constraints. Those differences are highly reflected in the RTL. When you change a target implementation under different constraints, RTL is completely different. As your model, as a single design evolves over the design process, the RTL is constantly churning. With the TL design methodology, a lot of that churn and those differences are absorbed below the verification model. So that's all very, you know, high level picture. We're going to focus on a couple abstraction mechanisms that are implemented today. These represent, I would say, about 2/5 of the overall vision for TL design. And they're implemented in there's an incremental approach to introducing these abstraction mechanisms. So today's implementation is a very you know, there's a very significant productivity benefit. And as we add more mechanisms for abstraction, there's sort of a synergy between all these things, or among all these things. And we really can get to a much, even more productive design methodology than I had imagined coming into this. You know, if you had asked me, say 15 years ago, probably, if I believed that the top-down design methodology was even possible, I would have said no. You know, it's you'll never get there. You can't start with an ISA specification and get to an implementation. As I've, you know, been focusing on design methodology and on these abstraction mechanisms, and gotten experience in the industry and with these mechanisms, I absolutely believe it's possible. We even have demonstrations of this today, and I think as the technology evolves, it's going to become more and more feasible. Okay, so starting with timing abstraction, which is embodied in this pipeline concept. So the pipeline is a fundamental construct. It represents a free-flowing pipeline, or an abstraction of time. So let's explain this through this example, which is a computation of Pythagoras' theorem. So it's a fairly deep computation. We're going to distribute the computation over 3 cycles. We're going to ignore the fact that square root could never be done within a cycle. So, you know, you square a and b, you add them together, you take the square root, and you get the distance c. This diagram is how you would draw the circuit with an RTL mentality. Thinking about that same circuit in a timing abstract point of view, TL point of view, we give ourselves a pipeline and we stick the logic in the stages of the pipeline. You'll notice here I haven't drawn the flip-flops. The flip-flops are implied by the fact that we have, I'll say, a signal, a pipe signal, going from stage 1 to stage 2. It needs a flip-flop to get there. You can take this diagram and directly translate to the TL-Verilog representation, which is on the right here. You can see it's a nice compact representation of the pipeline logic. Just looking quickly at the system Verilog, you can code system Verilog, you know, a million ways to skin a cat. This is one of them. This is essentially following Intel's best practice. And you see a nice code reduction. And that code reduction obviously has some very nice productivity benefits, fewer lines of code, fewer bugs, etc. But the real benefit, kind of going back to what I had said earlier about the churn. So, you know, well, if we need to take this design and re-implement it with different constraints, right? So maybe in this new implementation, A is available in one corner of the silicon and B is somewhere else. We have to bring them together. We have to get A over to where B is, so we need a cycle of transit and, you know, another cycle of transit here. The change, unlike the RTL, is very simple. We just have to, you know, literally in the code, move this expression from stage 1 to stage 2 by giving it or stage 1 to stage 0 rather, by giving it a @0, and likewise for the square root. The important thing being that these ats, which is where the change happens, are in this arrow. They're a form of mapping. So the behavioral model understands that we have a pipeline. It understands we're doing a computation within that. The code has both. It has the behavior specified. It has the mapping specified, the timing, which is the ats. And from that, we get the implementation with the flip-flops.
So
can I
yeah,
yeah,
jump in anytime.
I'm curious because we have a very similar representation in CIRCT, and
okay.
I'm curious how you handle feedback in that, or is it forced to only be feed forward?
Yeah, we'll get there.
Okay.
Yeah, so just hold on to that question. But I am very curious how you model this in CIRCT. Like I said, I've only scratched the surface of the introductory information that's available about CIRCT. So I'd definitely like to get to those deeper conversations. So just looking at this example at the code level, you know, when you're making these changes at the register transfer level, they're very disruptive. They're, you know, prone to bugs, etc. Kind of depending on your coding methodology. But again, this is kind of Intel's best practice. Okay, so that's the basics of pipelining and timing abstraction. Now let me introduce validity. So, you know, most hardware circuits, most of the time, are essentially sitting idle. The gates always exist. They're always receiving inputs, producing outputs, but most of the time those outputs are meaningless. And TL-Verilog gives you a mechanism to capture that understanding. And the way we do that syntactically for this example is shown on the left. So basically we're taking all this, sorry, I can't click there. Taking all this logic and putting it under this when condition. So this reads when valid. The valid is just a signal, could be any signal or pipe signal. And so it's, you know, it's going to be assigned to some expression. From that, we get the knowledge of when there's meaningful computation, which makes debug easier. So, you know, the actual tools that are all based on Verilog tool flows inject X when, you know, when we're declaring that the values are meaningless. And from that, you get waveforms that, you know, hide a lot of the cruft, highlight what's meaningful in the trace. You can clearly see the pipeline nature of the signals here. your designs are just fundamentally cleaner with additional information. You get additional error checking in current implementation from X propagation. If you're consuming something that you think is meaningless, that will propagate. And clock gating, which is on the next slide. So most of you probably understand clock gating and understand this pretty intuitively. When your computation is meaningless, there's no point driving the clock to the flop to carry that meaningless value from one stage to the next. So from that knowledge of validity, we can introduce fine-grained clock gating on the conditioned signals.
I'm not very familiar with the details here, but I've heard that there's some challenges with clock gating because you end up getting like the edges are not stable and you end up having to use specific kind of gates to do this kind of stuff. Is fine-grained clock gating actually pervasively
good?
Useful, or is it more complicated?
Yeah, I mean, it very much depends on the target technology, or even whether this is an FPGA implementation or an ASIC implementation, right? So yes, every design team will have their own methodology, their own constraints. So this is an area where the particular project methodology has to come into play in the generation of the underlying, the resulting circuit.
Yeah, but I mean, to the flip side of it is, it also seems as something that could be very global in terms of impact, because I imagine that a lot of things, a lot of wires are wiggling that don't actually need to, and so
in the case that you are. I'm not sure what angle that question.
Well, I guess what I'm saying is, it seems like in most designs, or in a lot of designs, there's a lot of silicon that's not being used at any given time, and so fine-grained clock gating could be a huge win. Have there been any studies about that, and have you?
So I don't have good data about it. My experience in the industry is, generally what happens is clock gating is an afterthought, right? The first thing is to get your model functional as quickly as you can to enable your verification team.
And then turn off huge blocks and, to save power in very specific ways, right? And
yeah, I mean, you sort of first do the very macroscopic clock, power gating and, macroscopic clock gating to turn off big circuits, like you're saying, with the goal that you're going to get fine grain over time. And then what happens is your design solidifies before you get a chance to do the fine grain clock gating. Your implementation team's been churning on the implementation for a long time. They don't want disruption of change. The clock gating circuitry can have, timing impact and area impact, and that's not getting baked in up front. So then you try to add it in, and it's very disruptive, and eventually your management says, you know what, we're just going to back away from our initial power target and get this chip out the door. With this approach, the clock gating is in there by default from the start, and then you go in and improve it.
Yeah, well, so again, I mean, what I'm observing, or what I'm imagining here, is that this could have a really, you have a structural advantage, right? Because you have knowledge of the enable lines and things like this baked in at a level of abstraction that allows you to generate that. And so I was wondering if there's any data or any studies or any experience that shows that this provides a big win.
Yeah, at this point, it's intuition more than data. Okay. I'm trying to think. Well, there was a similar thing with reset where I do have data, but I don't have good data for clock gating. But yeah, I mean, theoretically, sure, you throw a switch in the compilation process and disable clock gating, and then you can do a comparison and figure out where, oh, we're having timing on this path with clock gating in, but without it, it's gone. Let's focus there and fix it.
Yep. Cool. Yeah, interesting.
Okay, so now I'm getting into kind of this question of how I deal with feedback, feed-forward interactions between pipelines. And I'm going to get into that gradually, starting with this example. So this circuit is computing Fibonacci series, which I'm sure most people are familiar with. Every number in the series is sum of the previous two. You start with 2 1 values. So 1 + 1 is 2, 1 + 2 is 3, etc. The implementation of that circuit is here. So we have to, so we're computing a number every cycle. and that number goes through 2 flip-flops. So we have the previous value and the previous. Here we're looking at a snapshot in time where we're computing the value 5 in the sequence as the sum of 2 plus 3. So we need to be able to start off the circuit with 2 1s. So we have reset coming in. So while reset is asserted, 1s are being driven into the number. And then as soon as we deassert reset, we have the sum 2 feeding now into the the resulting number. And every cycle thereafter, we're adding the previous number, previous number, producing that result here.
Don't you have to reset the other flip-flop as well? Because if you have
actually, no, you're running the clock during reset. So you feed in the reset, you feed in the one here, the clock is running, that one's propagating through.
Oh, I see. So the one is the output of the adder. Yeah, okay, I get it.
Yep.
Sorry.
Yep.
You do have to make sure that you hold reset for at least 2 clocks, though.
Yeah, correct. Yeah, got it. Yep.
Yep, and that's, I don't want to get too much off on a tangent. I wasn't really intending to talk too much about reset, but that is a value here. Many design teams or design methodologies to reset every flop, as you were kind of implying. And there's an overhead to that, depending on your underlying technology. Most flops you don't need to reset. This is an example. And that's very easily exposed with a TL model. Okay, so just taking this diagram and kind of translating that to TL-Verilog, and I'm not going to focus on TL-Verilog syntax, but just to get a general idea. We get this, so we've got the ternary operator as our mux. If reset 1, otherwise take the sum of these 2 values. So this sum expression here is our adder, which is taking its values. And you'll notice there's no flip-flop explicitly in this code, similar to our pipeline example. The flip-flops are all explicit. There's never an explicit flip-flop in TL-Verilog. It's all based on the timing, right? And here we're saying ahead by 1, which requires a flop. Ahead by 2 requires a flop. I can't remember if I have another. No, I don't. So I've shown this here without explicitly drawing a pipeline, but the better or more explicit way to code this is to explicitly have this logic in a pipeline. And these numbers are pipe signals. Any questions on that? So further explaining by example, this example is showing the logic for an operand mux that would be part of a CPU pipeline. So our CPU has an adder in stage 4, apparently. We need to figure out what to feed in as the A operand. That operand could be coming from a number of places. If we're doing an immediate add, maybe this, and this isn't any particular ISA, that add might be coming from an immediate field in the instruction itself, which would be this immediate data. It might be coming from the register file, which would be this path. This register file is kind of a 2-cycle delay, so we need a register bypass. If this A operand is the register that was produced by the previous instruction coming out of the ALU, we need a bypass path here. And I'm assuming in this architecture that we can directly feed data from memory as the op-A value. So we have a path from memory into this mux as well. So we have the expression here for the mux. I've actually put this under a valid condition, but that's not so important here. It's all part of the instruction pipeline. In stage 3 of the pipeline, we have this mux expression, which is a chained ternary operator using Verilog syntax. Under these various conditions, we're selecting the various legs of the mux. And what's important here is what's feeding in to each leg of the mux. So we have immediate data. We have the bypass path, the result of the ALU. And here we have an ahead by 1 result. So this is saying, I want the result from the instruction that's 1 ahead in the pipeline. That gives you this. For the register file, we're reading from the register file, which is in stage 5, back to stage 3. So this is the register file that reflects all of the instructions up to the one that's 2 instructions ahead in our pipeline. That's giving us an ahead by 2. And the memory is coming from a different pipeline altogether. So this is, the pipeline stages are numerical, and we give our reference as a relative numerical offset, basically. So we're reaching into the memory pipeline with an offset of 5. So our context is stage 3. So this must be coming from stage 8 of the memory pipeline. So that's how we express. Go ahead.
So it seems to me like what you have here is not really RTL, but it's still very explicitly timed at the cycle level.
Correct.
Or are you assuming that you could implement this by a kind of an elastic style by changing which cycle or how the pipeline is implemented?
Yes.
Changing exactly which cycle things happen on, or are you explicitly talking about thinking about cycles here?
Right, right. And answering that more generally, right, I think philosophically my approach differs from many abstraction approaches in that my approach is to start from RTL. It's, in some sense a broken methodology because it's just not practical to do that anymore. But, you can design circuits with RTL. We have complete design flows that work. So my approach is to incrementally evolve from RTL to where we want to get. There are other high-level approaches that start with, hey, we want to do this, in a true elastic sense, and timing abstract in the sense of we're not cycle accurate. And then how do we get from there to an implementation? I'm coming at it the other direction. So my initial focus is what can we do within the realm of time of cycle accurate, being explicit, and then, then go from there to the next step. So yeah, I have the next step in mind. That's not my focus.
Got it.
Certainly as a first step of that, you could actually, let me get back to this point after I after I do the punch for this slide. So this is the expression of this MUX. Now this scenario is, what if we have a timing path here that's broken? How do we fix it? So let's say, we just don't have time to do this MUX in stage 3. Maybe the path from the register file doesn't have time to go through the MUX. How are we going to fix that? One possibility is we take that MUX and we move it to stage 4. So if we're just wholesale taking the whole MUX to stage 4, how do we do that with this expression of the logic? Well, MUX is moving to stage 4, so we change the 3 to a 4. What else do we have to do? Well, I said earlier the ats are purely part of the mapping, meaning they're not behavior. So the answer better be nothing, and that is the answer. We move the MUX. The reason these references are all relative is exactly to preserve the overall function. So we're delaying the MUX. We have to delay all of their inputs to preserve the functionality. So this, bypass comes from the right side of the flip-flop instead of the left side of the flip-flop. The register file gets an additional flip-flop to get to stage 4. Memory reference is coming from stage 9, etc. So this is how, this example is illustrating the various scenarios of feedback, feed forward. I guess we don't have feed forward here, but and interactions among pipelines. Getting back to the earlier question, of truly doing this timing abstract, you could certainly imagine that the designer doesn't care to specify the precise stage of the MUX. They just want to express the logic. So don't specify the at, right? Leave it just behavioral and let the tools figure that out. Current tools don't. Current tools require an explicit value, but you can certainly imagine that the model, essentially, you can imagine that the mappings from the behavior to the implementation are optional, and if tools are smart enough to make those decisions, they can. Any questions about this example?
Can you use symbolic constants in those cycle references?
So the approach that I take with the tooling is there's sort of this set of capabilities that are implemented, in a clean, proper way. And then I use macro preprocessing to hack stuff together. So the current answer to that question is in the macro preprocessing, which is very hacky and messy. It was meant to be quick and dirty. It was dirty and not quick, but that's what we have. So you can define a macro for this for, and a macro constant, and use macro preprocessing to construct your circuit. And you can do the same thing for these relative references. So if you do want a design that's elastic, you can parameterize the timing of the interactions. Any other questions? All right.
So part of this elasticity question is input validity, like propagation of valid signals together with the data, right? So,
right.
I assume that all possible just to bundle.
Yeah, so the approach I've been taking, there are other languages. There's SteveHoover, there's Pyrope. Maybe there are others. Those are the ones I know of that sort of bake in the ready valid handshake. I don't bake it into the language, at least not currently. I don't have a very clear vision on doing that. But as you'll see in the next example, I'm providing the mechanisms that enable you to build library components that bake that in. Right. So that's the approach I take with kind of the ready valid data flow kind of modeling, is to give you the mechanisms so that you can build the library components to do that. So anyway, that's a great lead into this example. So back to our Pythagoras' theorem pipeline circuit that we did earlier. Here I'm going to illustrate, maybe we start with this as a free-flowing pipeline, but then we decide we want to be able to stall. So how do we add stall to this network or this logic? Well, we want the ability to stall, means we need to be able to hold on to the values in the flip-flops. I've drawn that here explicitly as recirculation muxes. You can do the same thing by controlling the enable for the flip-flop. I prefer to show the explicit recirculation because, in a timing abstract sense, TL modeling, the flip-flops are a mechanism for timing. All right, so I always think of the flip-flops and diagrams as free-flowing, so there's no functional clock gating. So I'm choosing to draw the recirculation explicitly, and then we need a stall signal that's then going to control those to force the recirculation. So in a TL sense, these recirculations break the pipelines because pipelines are free-flowing. These are not free-flowing, so we need to break the pipeline into essentially a pipeline for every stage in this stall pipeline. And if I just take the circuit and directly express all of this logic in TL-Verilog, I would get this. I'll give you a second to look at it. I'm not going to go through each of these logic expressions, but I'm, just literally taking this diagram and translating it. So now I'm going to do a bunch of transformations. So the first thing I'm going to do is I've taken the expression for these two muxes. I'm going to jump back and forth here. So this is what I originally have. I have, sorry, not these two muxes, these, the squaring of A and B. So I have these two expressions here, one for A, one for B. And, oh, I'm sorry, that is the mux. Okay, so a squared is here, b squared is here. This is the mux, taking the a squared and b squared from the previous pipeline stage. You know, the numbering of these stages is basically arbitrary. I've chosen to number the stage of these muxes as 0 and of the logic as 1. So in stage 0, I've got this mux that's grabbing from the calc 1 pipeline stage, the a squared value, and likewise b squared, or the recirculation of the a squared, or controlled by the stall. All right. So the first transformation I'm doing is to make this expression generic. I have the same mux expression for both of these. So I'm going to replace the actual signal names with any. So this says anything that I need in stage 0 of this calc 2 pipeline, I can produce through a mux expression that's grabbing the same named signal from the calc 1 pipeline. And I've done the same thing here. There's only one c squared or c squared value. So it didn't really simplify the code, but the same transformation. Now that I've made this transformation, I can take these any expressions and pull them up. So I've separated them out. TL-Verilog has this property that I call, what do I call it? Lexical reentrance, which always sets off my Amazon Echo. There she goes. That allows me to specify logic in a certain context, and then later in the code, re-enter that context and specify more logic in that context. Doesn't seem like a big deal. You're going to see it's very valuable. So now that we have pulled this expression up, these expressions up, you'll note that these expressions are completely generic. They have nothing to do with the actual computation in the pipeline whatsoever. Excuse me. These are just expressions. Alexa, shut up. These expressions are just an expression of the stall nature of the pipeline. So now that I have these in a generic way, I can bury them again in an ugly form in a macro that expresses the stall nature of the pipeline. So at this point, I have code that looks much more like what I started with. So this is what I started with no pipelining. And this is what I ended up with the stall pipeline. We could implement a back pressure pipeline or some other control mechanism on the pipeline and bury that in a macro and just magically transform this stall pipeline into a back pressure pipeline, for example. So what these mechanisms allow me to do, the lexical, say quiet so I don't key off my echo, my dot, reentrance and the any expression, which is the transactions essentially. They're allowing me to put this flow behavior into generic library elements. RTL in contrast, it's what would be the term? I wanted to say black box, but I mean everything inside of a particular boundary must be expressed in the module. You can do ugly things with macros, but you really can't do the same kind of thing with RTL. So just sort of taking this concept, excuse me, a step further, we looked at a stall pipeline. You can do the same sort of thing with other, other components that are carrying data along and computing on the data as it goes. So other transaction flow components. So stall pipeline, FIFO, you can do phase-based logic in TL-Verilog. I've got a ring here. Free-flowing pipelines are kind of degenerate in TL-Verilog, arbitration, queuing, etc. So with a library of generic components, I can quickly stitch together a microarchitecture like this. This might be a, sort of a ring architecture where you've got some packet or flit coming in that gets queued up. It gets sent off to its destination. It might be for the local node, so it might go through a local ARB, etc. So you can construct these very quickly. And then with that higher level context, then put your combinational logic in place. So header decode, I don't know, register dependency calculations, whatever it happens to be. So that combinational logic gets placed through these scope constructs. So what pipeline is it in? What stage is it in? Into the context that's established by instantiating these generic components. And that implements your logic. So we've kind of decoupled the flow of transactions from the transaction logic that's combinational. So just to sort of talk through what this does for us, let's again use a timing example. So let's say this combinational cloud right here. Actually, before I explain that, so let's ask the question, what data is actually in each element of this FIFO? Right, and the answer to that, you can look at it the same way as the question of what flip-flops do I need in a free-flowing pipeline to get from one stage to the next? It's the fields that are needed at the output and available at the input. So, if back to the scenario now, I have a combinational logic cloud that we have timing issues with. One potential way to address that timing problem is to move that combinational cloud from the output of the FIFO to the input of the FIFO. Do that computation before you shove the flit or whatever it may be into the FIFO. So we move that cloud. The impact of that is that previously the definition of what's in the FIFO could be determined by this cut line, right? Stuff that's produced on the left, consumed on the right, needs to go through the FIFO. After this migration, the cut line is different, and that new cut line then defines what goes into the FIFO. Let's go through another scenario here to illustrate the benefits. This is something I've had experience with in industry, right? You design all of your logic, you're in the very late stages of the implementation of the design, and your reliability team comes back and says, we've determined that the error rates are just too high in the FIFO and the ring. We need to fix that. The architecture team says, all right, well, we're going to fix that by adding parity. Simple example, we're not doing CRC here. So the architects have said, all right, you need to add a parity bit. We want to protect both of these structures. So instead of adding a parity calculation on both, we're just going to add it this one place, carry that parity through both structures, and check the parity at the output of arbitration. Okay, so how do we implement that? Well, in RTL, you've got to actually carry that bit through all of these structures. In TL-Verilog, you add the parity computation so that you have the parity available, and you need the parity check here. So you put the parity check logic here that is consuming the parity, and the tools take care of it, right? The tools say, I need parity. How do I get parity? Well, I go through this any expression that takes me back here and here. Oh, I need parity here and here. And it just follows that graph backward until it finds parity here, and then it drags it forward through that flow. All right, and I need to escape out of here just so I can see how I'm doing on time. Pretty good. So we've got 15 minutes basically for discussion. That was all I wanted to talk about in terms of modeling and abstraction mechanisms. So are there any questions or thoughts on, in particular, how all this relates to CIRCT? As I said, 15 minutes is certainly only going to scratch the surface. I hope this leads to further discussion, but in the time that we have, I'm open to hear thoughts.
So there are another, so if in the circuit design,
Is there any way you can speak louder?
Oh, sorry. So if we have more control logics than expected, how do we deal with this design methodology? I can see in design in this way is very good for data flows, but if we have more control and stores to this is possible to resolve.
Yeah, I mean, that's true. When you take control logic and directly express it in a timing abstract way, it doesn't really get any simpler. But this whole ability to capture the control logic is what's expressed in these flow components. So the ability to put this control logic that is controlling the sequencing of your operations or the flow of the data, or most control logic is there to control the flow of data and to sequence things. And when you have the mechanisms that enable you to put those into generic components, then suddenly you're not actually writing the control logic. So the ready valid handshakes that we mentioned before, yes, TL-Verilog doesn't make the ready valid handshake logic any simpler, but it does enable you to express it in a way that you can put it into a library element. And then, all of these flow components that are depicted here basically are using a ready valid handshake to control the flow of the data. You never have to code that ready valid handshake explicitly. You just instantiate these components and plug them together.
I see. Really amazing. Thank you.
Yeah. So one other property of validity in circuits like that is that you can do replay mechanisms, right? So you can instead of stalling something, you can say, I go ahead and compute it, but at some point you don't commit it. So you kill intermediate computations, right? So so this way is maybe more more efficient, because there is non-zero probability you will need that result. But how do you deal with how would you showed example with a stall? Can you actually do something like replay or kill?
Yeah, I mean, I have an example of a flow component that is a what does it do? It's doing a, well, I'm not sure how to describe it generically, but one use of it is to perform an add with an addition that's not perfect. There are cases it doesn't deal with perfectly. So you do this quick add, and if you determine that that quick add wasn't computed properly, then you replay that add, and that kind of mechanism can be coded up in a generic way. I'm not sure whether that answered the sort of scenario you have in mind or not.
Yeah, it's
but
it's possibly do, but
validity itself, right? There's nothing in the modeling that the tools are figuring out. When are things valid? There's no high-level synthesis here, right? Everything is explicit. So the tools are not using the knowledge of, doing any analysis of the data flow to determine validity logic. You're expressing the validity logic, and the validity mechanism is just a way to tell the modeling there's nothing here, nothing meaningful. So there's no, you know, HLS kind of data flow machinery. It's just the mechanism for the designer to say, hey, this is garbage.
So you mentioned that this is quick and dirty macro mechanism you did was done to make it quick. So how does it does it implement it these days? Like, have you stuck with what you had? Will moving to a different IR benefit you?
Yeah, oh, definitely. Yeah, I mean, I can see a lot of benefits of having you know, having this all formally modeled. I mean, essentially the macro environment gets you the demonstrations that you want, that you can parameterize things, you can make your modeling simpler and more flexible, and retarget designs to different implementations, all with macro preprocessing. But macros are text substitution, right? There's no actual knowledge in the system of what the model is doing with this level of abstraction. So getting all of that knowledge into the actual tools, into an IR, then you can start to manipulate it. That's definitely where we want to be. But yeah, now I use macro preprocessing for things like the parameterization for loops. You know, and as we mentioned, the parameterization of pipeline stages is very powerful. You know, code construction generally.
Is there any particular concerns in this model that you have to deal with for initialization and pre-reset behavior?
So I wouldn't say concerns. I'd probably say some benefits potentially. So I don't have slides handy for reset, but so reset is another area where different teams have different methodologies. You know, we tend to have a methodology that says we're going to hold reset for a minimum so many cycles. We're going to verify reset by doing X propagation. Yeah, trying to figure out what I want to emphasize here. Yeah, so generally, when you reset the machine, you're basically saying, you know, there are no valid transactions in the machinery. Get me into a reset state. All the queues are empty. In modeling things in transaction level model, I tend to treat I tend to treat reset as if there are reset transactions flowing through the machine when reset is asserted. So instead of like simultaneously blasting everything to invalid, I simultaneously blast everything to the machine is doing reset transactions. And these transactions march through the machinery and get you to a reset state. And doing things that way, you sort of have this clean, all right, as long as I'm doing reset for so many cycles and this reset transaction is going to get through the machinery before that, you know, time period ends, it's going to go clean things up. And that means I don't have to clean things up on, you know, cycle 0. It means you clean them up when that transaction marches through. And that helps you get rid of reset flops. And, you know, sort of this, it's cleaner in the sense that reset becomes timing abstract, right? So it's not blast everything as it exists. It's we have this higher level model that has pipelines and structures, and you know, there's going to be a reset transaction that goes along before any valid transaction, and that reset transaction is going to get us to stable. So when you're doing reasoning about the modeling at a higher level, a timing abstract level, you just know that transactions have this combinational logic. Well, there's a reset condition that goes into that combinational cloud that is timing abstract, that that it's going to set states that it drives to a reset value. It's hard to explain in a definitive way, but I think it's fundamentally that you can do reset in a timing abstract way as well.
Does that mean that you naturally insert pipeline registers on the reset as well? Because it's not a privileged concept. It's just,
well, yes,
yet another signal in the system.
That yes, reset is it might be encoded or it might be its own signal, but yes, it's a pipe signal, and therefore it participates in the staging of the transaction through structures.
Do you have any? Oh, go ahead.
Sorry, go ahead.
No, please.
So I think I understood the overall model, but I have one question which I'm not sure if anyone can answer. But I understand, like, at the chisel level that you get similar abstractions, kind of building from RTL into libraries, so you get all of these pipelines and rings and similar mechanisms, but you get there through very different approaches, right? And what I'm not sure is, in the end, what are the benefits of TL once you are able to build those libraries? And so, for instance, I could argue the case, for instance, with something like Chisel, maybe you have more control of how exactly you're going to manage the building and interlinking of those abstractions. Whereas in the transaction level, I would imagine that depends more on the compiler, so to speak. So maybe the user doesn't have as much control. So I'm not quite sure how I would compare the two models. Do you have any insight about that?
Yeah, I mean, a couple of things I would say. I mean, yes, the approach that Chisel takes with Scala is a better, it's a much more capable approach for code construction than the macro preprocessing hack that I use. I will say the macro preprocessing hack has the advantage that it's something that a logic designer can understand, where Scala might not be. But if you're doing anything substantial with it, the macro preprocessing gets really ugly really fast. Chisel's strength comes from the code construction, all right, and that's all based on software generating the hardware. The software, whereas with TL-Verilog, the model, right? It's about the internal representation, right? The model is captured in a timing abstract way. You can interact with those data structures if the right APIs are available. Whereas in Scala, and others might have different opinions, but it's software. It's not. I would think it's much harder to algorithmically interact with the model at a higher level. You're using software and the flexibility that software gives you to be able to flexibly construct the hardware. But it's just a process to get from your software to a hardware implementation at the register transfer level. And that's the representation that you can work with. So if someone knows that I'm speaking out of turn, speak up. That's my impression.
I get the sense that you have in mind a model of the Chisel side, and I'm not saying you're wrong, but where it's very imperative, so you don't have this kind of declarative model where you say, oh, I expect this overall behavior of how the things are connected. And I don't really have any good opinion on whether that is true or has to be true, so I'll let other people speak about that, but at least thanks for verifying that. That's a good approximation of what you're saying.
So maybe this is a little too nitty-gritty, but I was curious how you would integrate a pipeline you have here with data sources from different clocks. Like, is that dealt with outside the system?
So there's currently no support for clock domains in current tools. So the current tools are implemented such that you use TL-Verilog within the context of a system-Verilog module. So you do your higher level stitching module hierarchy with Verilog, you do your logic with TL-Verilog within that context. You tend to develop much larger modules that contain a lot more logic, but where you have boundaries that are, every design team has different terminology for this, but that whatever unit you're sending to synthesis, right, you need a module boundary there. You would do that module boundary in Verilog. Wherever you have a clock domain crossing, the actual clock domain crossing logic would just be Verilog libraries today. But ultimately, you can build libraries of components that cross clock boundaries. You can, instantiate those as TL-Verilog libraries, and it really the only missing construct there is being able to specify the clock domain as a scope. I haven't done that, just not there yet, right? Building from the guts of the logic outward, but it's really not a significant step to introduce a scope that is clock domain, and you can't reach from one clock domain directly into another clock domain, or if you do, that implies a clock domain crossing logic. So that's the answer I have today.
So do we have any other questions? Or shall we, in the interest of time, call it? But thank you. That was very interesting. Enjoyed it.
Good. Yeah. And like I said, I'm happy to, I hope this is the seed that fuels more conversation. I'm here if anybody wants to reach out. All right. Thank you all.
All right. Yep. Thank you all.
Bye-bye.
See you.
Bye, guys.